Hey, nice to see you here. Welcome to my talk. I'm Manuel, and today I'll be talking about intermediate mass ratio inspirals. And all the results I'm discussing are described in our last paper posted on the archive last month. IMRIs are basically binary mergers that sit between normal binary mergers and extreme mass ratio inspirals. The typical mass ratio for this object is 10 to the minus 4, 10 to the minus t, 2, and several types of them exist. Today we will be talking about intermediate mass black hole paired with a stellar black hole, and we will be exploring the mass range between 10 to the 2 and 10 to the 5 solar masses. The idea behind IMRIs formation is very basic. You have the formation of an IMBH first, and then some stellar mass black hole or stellar compact object reach the innermost region of the cluster where this IMBH is contained, and form through dynamics IMRIs, even multiple times. But the reality is much more complex than this, in fact, because the IMBH formation process, for instance, can affect strongly the population of black holes, thus affecting inevitably also the formation of an IMRI. So in a series of papers, we have been studying how IMBH might develop in star clusters, exploiting this suite of Monte Carlo simulations. Please refer to these papers if you are interested into details about this. We basically found that IMBHs can form through two main scenarios, A and B. In the A or fast scenario, you have the most massive stars that start colliding with each other and build up a very massive star that collapses into an IMBH. In the slow scenario instead, you have the normal dynamics formation of ordinary stellar mass black holes that start interacting and ejecting themselves from the cluster until to the point when just one or two of them are remaining, and one of those start growing via stellar feeding. In both cases, which by the way are associated with different formation timescales and different environments, in both cases the buildup of the IMBH leaves behind just a handful of black holes, just one or two. And so the IMBH process affects strongly the probability for an IMRI to form and take place. So with these scenarios in mind, we decided to study a very simple idea, a very simple scheme, a single IMBH in the center of a star cluster that is modeled through its mean field, and two stellar mass black holes that are orbiting around it. We are not assuming any hierarchy on this triple system. We want just to see if these orbits interact with themselves and trigger the formation of an IMRI. We ran 28,000 direct embody simulations using the ARGDF code that implements close encounter treatments, post-Newtonian formalism, and an external potential. And to explore the parameter space, we varied the IMBH mass, the black hole mass spectrum, and the orbits of the two black holes, and finally the metallicity of the black hole progenitors. This is a summary of all our choices, and if you are interested in the details, please have a look at the paper or contact me after the talk. We found many IMRIs in our models, and to describe the evolution of such IMRIs, the best way is to show the time evolution of the semi-major axis and eccentricity of the most bound pair in this triple configuration. So in this specific example, we see that the evolution is dissected into three main phases. Phase A, where we have a chaotic interaction between the two black holes and the IMBH. In this phase, it's very difficult to say who is who, because the two black holes exchange continuously with the IMBH. And then one of the black holes is pushed on a wider orbit and starts exerting some kind of secular and periodic perturbation onto the innermost binary that in fact result into an evolution, a weird evolution of the eccentricity of the binary, as you can see here. And this phase, which is the long-lasting one, culminates with a maximization of the eccentricity that reaches values so close to unity to allow gravitational wave emission to kick in and dominates the last phase of evolution of the binary down to the merger. This is just one of the examples we have in our simulations, and is just to give an idea of how an IMRIs formation proceeds. Overall, we found 20 to 30% of mergers in all our models, regardless of the initial conditions. And when you dissect this merging probability, into different IMBH mass bins, you see that the resulting relation is non-trivial at all. We have a kind of maxima value for the merging probability at IMBH masses of 10 to the 3 and 10 to the 4, although with a huge scatter that depends mostly on the initial conditions. So then IMRIs seem to form quite frequently, especially in this mass range. And we've been looking for peculiarities of these IMRIs that can tell us something about the evolution of the IMBH or of the cluster that is nursing it. So what I'm showing in this series of panels is the mass distribution of merging black holes in field steps, and overlaid to that I'm showing the initial adopted stellar mass distribution. As you can see, in all the cases the merging black holes tend to map out the adopted initial mass function, meaning that we can use IMRIs to infer and get insights on the black hole distribution, the black hole mass distribution in the star cluster, and to get insights on the effect of dynamics onto such a population. Whether, for instance, black holes preserve their stellar evolution mass spectrum, or they arrange in a more exotic mass distribution because of effect of dynamics. Another important parameter is the eccentricity of the IMRI, especially when this is transiting into frequency bands of interest for gravitational wave detectors. So in this case, I'm showing the average eccentricity for different values of the IMBH mass, and for different values of the frequency band, millihertz, decihertz, hertz. And what we see is that regardless of the mass of the IMBH or the initial conditions adopted, all our IMRIs on average have an eccentricity below 0.1 when transiting in these frequency bands, meaning basically that our IMRIs are almost circular when we might be able to localize and observe them. And this is very important to assess the detectability of these sources. And then we have the IMRIs formation, we have the merger process, and then a gravitational wave kick can eject the IMBH out of the cluster, and thus limit the further growth of such object. So what I'm showing here is the so-called survival probability or retention probability for an IMBH with a mass of 2,500 solar masses and a cluster with a velocity dispersion of 5 km per second. For this value of the IMBH mass, I created a tree of mergers for different values of the stellar mass, the stellar black hole mass, and each point here is averaged over 100 mergers, assuming different values of the spins. As you can see in this specific case, whenever the companion black hole mass is below these 60 solar masses, which by the way is the maximum mass allowed for single stellar black holes, your IMBH will be retained with a non-negligible probability in the host cluster. So it means, if we want to enlarge a bit the picture, we can do the same kind of analysis for different lines, namely different values of the IMBH mass, and different panels, namely different values of the velocity dispersion of the clusters. And when you do this, we have basically one bottom line, that is, whenever the IMBH mass falls below 200 solar masses, it is most likely to be ejected whenever the companion black hole mass exceeds 10 solar masses. While if the IMBH mass is already of the order of 1,000 solar masses, then it's most likely to be retained upon merger with a stellar black hole unless the mass exceeds 60 solar masses. And this finding tells also us that if we observe today an IMBH in a star cluster with a mass of 2,000 solar masses, it's most likely that it didn't undergo major merger with the stellar mass black holes during its growth process. So it's something that it can be directly connected with the IMBH formation history. And another parameter that can be used in this respect is the spin of the IMBH. So what you see here is in colored points is the final spin after the merger of the IMBH, assuming that the initial spin was 0.1, 0.5 or 0.9. And we see here different values of the IMBH mass and the mass ratio in the IMRI. And as you can see, in this case, the merger event does not affect significantly the IMBH spin, meaning that from IMRI in these mass ratios, we can get insights on the natal spin of IMBHs. While if we go to lower IMBH masses and higher mass ratios, the effect of the companion spin is crucial in determining the final spin of the IMBH. And so we can use IMRIs to get, in this mass ratio range, to get insights on the overall spin distribution of stellar mass black holes in these kind of star clusters. Now the big question is whether we can observe these kind of sources, especially in our backyard. And so to address such question, we exploit our finding that IMRIs are mostly circular in the LISA band, for instance, in the millihertz frequency band. So we can calculate easily the associated gravitational wave emission and the associated signal to noise ratio. And in doing this, we assume a distance to us of 8 kiloparsec, which, by the way, is the distance between us and the galactic center. And we varied the mass of the companion paired with the IMBH. And as you can see, we found in the mass range of 10 to the 3, 10 to the 4 solar masses, a signal to noise ratio between 6 and 100, meaning that we have quite a good chance to observe IMRIs within these distance ranges. Now, the real question is whether we do have any cluster with IMBH candidates in this distance range. And in fact, it turns out that we have a bunch of them. We have, for instance, the most famous one is probably 47 TAC, which provided us with several controversial evidences of the absence or presence of an IMBH. And we also do have the Galactic Center that provided us with the mounting evidence for one or more IMBHs in the innermost 10 parsecs of the galaxy. So LISA might shed a light on the presence of these big IMBHs in star clusters and the galactic center. Not only we can get insights also on the presence of an IMBH in our close neighbor, the Large Magellanic Cloud, that is thought to host an IMBH in its center or in some of its young massive clusters. And in this case, if we repeat the calculation, we found that the signal to noise ratio associated with detection in LMC would be between 8 and 40. So still, it's possible to place constraint with LISA about IMBHs in the LMC. Nonetheless, we can go further out, but for doing this, we need to calculate the horizon redshift, which is the maximum distance we can reach with a gravitational wave detector. And in doing this, we assume a signal to noise ratio threshold of 15 and an observation time of 4 years. And we calculated this horizon redshift for different detectors. You can see here a summary of the findings. And then we can use this horizon redshift to evaluate the merger rate for IMRIs. That mostly, as you can see in this equation here, mostly depends on this term. That is a combination of factors depending on the physics of the IMBH formation, the dynamics of IMRIs, and the cosmic distribution of galaxies, star clusters, and IMBHs. Now, when you put all together, you can perform the calculation eventually, and we did it for LIGO. As you can see here, LIGO might observe up to 2 mergers of an IMBH with a mass between 100 and 200 solar mass. This also means that O3 might contain already one of such IMBHs, and we are really eager to see whether this is confirmed or not. LISA might gift us 70 events per year and shed a light on IMBHs with a mass below 50,000 solar masses. And in the next decade, the LIGO and the Einstein telescope can provide us and can deliver thousands of events per year, chasing IMRIs up to the dawn of star formation. And in this respect, is very worth mentioning that this year's and Earth's observatories in the future might enable us to observe IMRIs in multiband detections from months or years prior to the merger. So with this last slide, I want to leave you my main take-home messages. We analyzed IMRIs formation. We found that IMRIs have a merging probability of 20 to 30% in star clusters, and we have shown how these IMRIs can be used to shed a light on the interplay between IMBHs and stellar mass black hole, and on the IMBH formation process, whether it formed with an already large mass or from the stellar black hole mass ranges. And we have shown that we can observe this in the galactic environment, especially within the innermost 8 kiloparsecs from us, but also in the Large Magellanic Cloud. We made some prediction from LISA, but also for other detectors. We infer for LIGO the detection of one IMBH in every 2 years with a mass below 200 solar masses. And in the future, we think that Einstein telescope and the LIGO can observe thousands of these events and these sources up to the dawn of stellar formation. I want to thank you for the attention, and I hope you enjoyed the talk. Please feel free to contact me for any question and any comments. And I want to say bye-bye. Hope to see you soon in person. Stay safe. Bye.